The difference is that, as you know, small changes in the family of graphs which are expanders can make this family lose this property of expansion, and this is not the case of mixing times. Right. So we'll be talking about random walks. Okay. And another introduction to this talk is related to this remarkable fact that every finite simple group is generated by two elements. So it's a consequence of the classification of finite simple groups. There is no direct proof of this remarkable fact without using the classification. And then you can ask how efficiently these two such a pair of generators can generate all elements in your finite simple group. So it's not only true that there are two elements that will generate your finite simple group, but actually if you pick at random two elements with probability going to 1, when the size of your simple group tends to infinity, they will generate the group. So by talking about mixing time, it measures how efficiently you can generate all elements in your group. So it will be random walks on random symmetric groups. Okay, so the random will be the choice of generators, say two generators, and the same what we're going to say here applies for alternating groups. Yes. So that's why I started by talking about finite simple groups. And most of what we're going to see is the joint work with Harald Helfgott and Ákos Seres. Okay, so we'll consider a finite group, for instance, a symmetric group Sn, and we choose a generating set, and then we start to multiply at random these generators according to some measure mu. So the distribution on the group that you obtain after doing it m times, it's a nth convolution of this measure, and we want to measure how close we are to the uniform distribution. Right? So the distribution 1 over the size of the group, and we will take a difference distance between these two distributions, okay, L1, and we say that the mixing time is m if this distance is less than delta. Okay, so m is the smallest m which satisfies this inequality. So here we suppose that delta is such that it would be a non-trivial condition. So m, the smallest m, is called the mixing time. Okay. And we'll be talking here about infinite families of the groups. So the choice of delta does not matter for these results. Of course, there could be also, I could also give you, if we're talking about symmetric groups, so it's natural to give yet another introduction to the subject that you consider S52, M corresponds to your favorite way of shuffling cards, and then of course the choice of delta is important. So if you really need like a constant, say it's 1 over the Euler constant. Okay, very good. Okay, so this is the main object of the talk. We would like to understand what are the mixing times when for the symmetric group when we choose two generators at pair of generators at random. So as we said already, it's closely related to expansion properties. When m goes to infinity, well, this decays exponentially fast, and the speed is governed by lambda 1. However, if you fix delta, it's a much more interesting story. It's not just lambda 1 that will be relevant. Okay, so let me remind you definition of expanders. So for a graph X, which for us is finite, but what really matters for the definition is that it's locally finite, we'll define its isomorphic constant as follows. So for such a graph and for any finite subset of vertices A, we'll define its boundary as the set of edges with one extremity inside and another one outside of A. Okay? And the isomorphic constant will be the minimum of the relative size of the boundary divided by the size of A over all subsets in X, with the natural restriction that the size is at most, say, half the size of X. Okay, and the idea of expanders is having graphs with the large isomorphic constant, provided the degree of graphs is still low, that such graphs are highly connected. Okay, so maybe so the definition, a family of finite graphs Xn of degree k. Actually, what matters is that there is a uniform bound on degrees of all vertices in all these graphs of degree k, is called a family of expanders. Okay, if there exists uniform lower bound on all as well the constants of all these graphs, right? Such that h of all these graphs is bounded below by the C. Of course, it's a non-trivial condition for an infinite family of connected graphs. Okay, the quantity which is closely related to the isomorphic constant is the spectral gap for the discrete Laplace operator. So if we take a function on the vertices of the graph, say real value of L2, well, if it's finite, it's not a restriction, then the discrete Laplace operator, its identity minus the sum of the values over neighboring vertices. Okay, and so for finite graphs there is a finite number of non-negative eigenvalues of this operator, and the quantity closely related to H is the first non-trivial eigenvalue. Okay, so equivalent condition to the definition of expanders is that lambda 1 of all these graphs is uniformly bounded away from zero. Okay, so most of you thought for years about the notion of expanders. However, if you see this definition for the first time, maybe it's not clear why it's a non-trivial condition. So there are several I guess ideas one look at first trying to construct such a family of graphs. So for instance, if you look at this isometric constant for infinite graphs, okay, then you take the minimum over for this quotient over O finite subsets. Then for given degree, it's easy to understand what is the graph with the largest isometric constant. Okay, so for degree 3, it's a tree of degree 3. Okay, the graph of degree 3 with no loops, and it's an easy exercise that the isometric constant for this graph is equal to 1. Okay, that every subset has at least as many edges going out as there are vertices inside this this subset. So you might think that you as finite examples of expanders, you should look at finite trees. Okay. However, if you take a finite tree, if you remove any edge, it will disconnect the graph. So the trees are the best, like infinite expanders, and they are the worst finite graphs when we talk about the isometric constant. Okay, so it's just an indication that all these very well natural candidates won't work. Okay, so actually the first results concerning existence of such graphs were obtained using probabilistic methods, and I would like to explain this result in detail because it's very closely related to random walks on the symmetric groups. So the model of random graphs, where we prove that most of the graphs are actually graphs with a large isometric constant. This model is based on symmetric groups. So here is the model. We consider n vertices, 1, 2, up to n. Let us call them I, input vertices, and another copy of these vertices, also labeled by from 1, 2, up to n, O outputs. We consider the symmetric group as n, and then k elements in the symmetric groups by 1 by k. And the graph will be constructed as follows. So the vertex I in input will be connected to to the vertex phi j of I. Okay. In this way, we obtain a regular graph of degree k. Okay. And so let us call all the set of all these graphs x to n. There are to n vertices, and k. They are of degree k. And what is very important in this model that we won't count graphs with respect to the natural isomorphism relation. We'll say that two graphs are different if the permutations which define them are different. Okay, so also, so if we exchange permutation, they might define different graphs with respect to our counting.
Is that a regular graph? Is that?
Sorry?
Is that a regular graph?
Yes. So this is a regular graph of degree k.
Pi 1i and pi 2i are different, for example.
And no, they might be different.
But
We allow multiple edges. It's not a problem. Another, well, you also. Sorry? No, no. No, this is a bipartite graph. Actually, you might think that it's a very strange model because we obtain just bipartite graph. What if you could identify vertices in inputs and outputs, and in this way you obtain arbitrary graph on n vertices of degree k. Okay. I would like to present you in detail result about expansion, and it's easier to talk about this model, but it doesn't matter. The result comes also after this identification.
When you said that you were counting graphs up to, you were saying that two graphs are different if their permutation is different. Do you mean as an ordered set or as a non-ordered set?
Here as an ordered.
Right. So even if I just swap pi 1 and pi 3.
That's right. So obviously you obtain the graphs which are isomorphic.
Yeah, but that's.
So it's like the edges are labelled by the edges are directed and labelled by 1 to k. So you can tell which edge came from which permutation. It's isomorphic.
Yes, we'll be counting the permutations. Okay. So we have in this model we have S many graphs as there are k order permutations. Okay. So the result, which is due to Pinsker, says the following. So if k is at least 3, then if you count the number of graphs here such that the isomorphic constant is less than 1/2, and you divide by the number of all these graphs, then when n tends to infinity, it's equal to 1. Okay, so almost all graphs have large isomorphic constant. Okay, let me show you the proof of this theorem. So maybe we'll slightly modify the definition of the isomorphic constant, namely for the subset A in inputs, we'll define its boundary as the set of vertices in O which are connected by an edge with a vertex in A. Okay. In other words, it's the size of the image of this of A by all these permutations. So that's the this new boundary D prime A, and we'll define the new isometric constant H prime of the graph X as the minimum, the size of this new boundary D prime of A divided by the size of A, and we take the infimum over O subset in inputs with the restriction that the size of A should be at most half the size of I. Okay, so of course it's wrong definition of isometric constant, yeah, because size of the image is at least the size of A, so it's always at least 1. So please forget this definition as soon as the proof of the theorem is finished. We will use this H prime to estimate H, so it's easy to see that the right one is at least H prime minus 1. So what we're going actually to prove is that this H prime is at least 3 halves. Okay, so what is the proof of this result?
I'm just slightly confused about why you're going to call it D prime rather than D.
Pardon?
I'm confused about why you call it D prime rather than D. Is that because you're counting vertices and not edges?
It's no. So here it's very different, right? We are so yeah. First of all, we're counting vertices, but the most important is that here we consider only
No, I agree that H prime
subsets
is
which
different
are
from
in
H.
I.
I'm wondering why D prime is different from D.
Pardon?
I agree that H prime is different from H.
Right.
I'm wondering why D prime is different from D.
So here we're counting the vertices. Okay, and the previous one we were counting edges.
Right.
So I reminded this definition because later on I would like to talk a little bit more about the values of this invariance, and then it really matters which definition we consider. Okay. Right. So yeah. So what is the proof? So we want to estimate the number of permutation, which will we want to show the number of permutations which will lead to graphs with a small isometric constant less than 3.5. It's small, and compared to all choices, it will tend to 0. Okay, if we have a graph with isometric constant H prime less than this number, it means that you have a subset A and a subset B in O, size of B equal to 3/2 the size of A, and all permutations evaluated on A will take the values in B. Okay. So what is the number of such choices? Okay. If you want to check it out, call such choices bad choices. So we will estimate, well, first for one permutation, and so first of all for one permutation, so we have to count all the number of choices for A and B. Okay, so it's the sum of all subsets in O in I. The size of A is at most n over 2. Then number of choices for B in O, the size of B is equal to 3/2 the size of A. And now, given A and B, how many permutations do we have such that evaluated on A, they will take the values in B? So for the first element in A, the number of choices is the size of B. then for the last one, it will be the size of B minus the size of A plus 1, right? Okay, so that's the number of choices of the value for the vertices in A. Now, for the vertices which are outside of A, there are no restrictions. There are no restrictions. So the number of choices will be n minus the size of A factorial. Okay, so this is the number of choices for one permutation. If we have k permutation, we'll just k it to and take it to the power k. Okay, right. So let us rewrite this double sum. So let us take the sum over the size of A. So it will be from I equal to 1 to n over 2. So now the number of choices for A, it will be n choose I. The number of choices for B, it will be n choose 3 half I. Right now the size of B, this is 3 half I, so it will be 3 half I factorial divided the size of B minus size of A, it will be 1 half I, so it's I divided by 2 factorial, and here we have n minus I factorial, okay, and all this to the power k. Okay. Now, given that the number of all choices is n factorial to the power k, using this estimate, you can prove that the number, the ratio will tend to 0 when n tends to infinity. Okay, so that's the proof, and maybe also this result was similar results in different language or obtained maybe also by other people. Okay. Right, so this is the beginning of the story. Unfortunately, this proof does not generalize to does not allow generalization, for instance, for the action on the symmetric group, not just on elements, but also on pairs, on triples of elements. And these are results that we'll need later for estimating the mixing time for random walks on the symmetric group. So this kind of results you can obtain not by geometric methods, but more like analytic methods related to the theory of random matrices. Okay, but it's wonderful that one can present such a proof.
So corollary expands exist.
That's right. That's right, and they exist. However, and most of the graphs are expanders. I will actually maybe discuss later some consequences of these results, which you cannot obtain by other means. However, it doesn't give any indication how to give explicit examples of such families, and they were given by first by Margulis.
this tends to 0, what saves you is in power k, right?
Right.
But the n factor, I mean,
Right. Yeah. So maybe also right.
because it's not clear why you say liberty. Still. But okay, no, I think it's because of the two factors in front.
That's right.
Why you need k bigger.
But what is so now I'll talk a little bit what happened then in the subject, but maybe it's because we still have this proof on the blackboard. So one could ask about the best possible values concerning this expansion. So the way to understand it, well, we could talk about lambda 1, we could talk about isoperdy constant. So the way to understand what are the possible values, well, one should look at the universal cover of this graph about the regular tree of degree k. So as far as lambda 1 is concerned for finite graphs, well, you should compare it with the spectral gap for this Laplace operator on the regular tree of degree k. Okay, so here we consider family of graphs of degree k, and size of this graph tends to infinity. So the best what you can hope, so comparison between two gives you that lim sup when n tends to infinity. This is at most lambda naught of tk, and well, let me remind you that lambda naught of tk, it's 1 minus let me remind you, k minus 1 over k. Okay, so this is the best you can get for finite quotients. Now, if you look at the isoperdy constant, so it's the exercise for the regular tree of degree k, it's k minus 2. So of course the same comparison result would tell you that this is the best you can achieve, right? The subsets with the small boundary in the tree will give you subsets with the small boundary in finite quotient. But what is interesting that so the lim sup infinity that you can do better. Okay, so that you can actually prove that it's h of tk divided by 2. So the best you can hope for is k minus 2 over 2. Okay, so it's a completely different kind of argument. The subsets with a small boundary with finite graphs, they have nothing to do with subsets of the regular tree of degree k. Okay, and this result just with k over 2 is due to Bolobash using probabilistic arguments, and the slight improved bound with k minus 2, which tells you that the best you can hope for is half what you get for the universal cover. It's a result of it's a joint work with Bob Brooks. Okay, and this side, this condition on graphs that well, lambda 1 is at least as good as for the universal cover. So it's a story about Ramanujan graphs. Such graphs exist even for every degree, and it seems to me that there are So there are even for some degrees of K explicit construction of such families. It seems to me that this is unknown as far as the isometric constant is concerned. And with this respect, using this kind of ideas, you can actually prove that optimal graphs from the isometric point of view do exist. Okay, great. Okay, so after this proof, the way of constructing explicit examples were given by Margulis. Maybe you can take any group with property T. So let gamma be a group with property Cartan's property T generated by finite set S. So if gamma n's are finite quotients of gamma, then K graphs of these finite quotients with the choice of generators, which is the image of S in these finite quotients, the quotients are expanders. Okay, and so we get infinite families provided that gamma n's, the size of gamma n's tends to infinity.
You need residual finite.
No, you don't need residual finite.
Okay.
Yes.
You can take any group with property T, and you take any family of finite quotients, then there are expanders. The only to get it like non-trivial is that the size will tend to infinity. But
Yeah, no finite.
Yeah, but then I mean the question is what do you call expanders?
Yeah.
Either you call infinite family, but if you call finite family, then you must say the parameter because
No, I agree.
okay.
Yeah, if you the curve.
No, but it's fine. Gamma n tends to infinity.
Yeah, that's he didn't have that in his definition.
Right. And it's even more general. We don't even need to do that. You don't. Well, you can consider Schreier graphs. Yeah, you can divide gamma subgroups, channel normal. Great. So right. So T implying construction of expanders. Yeah, this is result of Margulis. Actually, in a sense, there is like a converse to this result. Namely, if you in a Cayley graph of gamma you find one expander with this time large lambda 1. So, namely, if you have lambda 1 of the sphere, unit sphere, strictly greater than 1/2, so I prove that then the group has property T. So somehow it's notion very closely related to property.
But you need all your links.
Pardon?
You need all your links, don't you? To have-
So here I said about Cayley graphs.
Oh, okay. So in Kelly graphs,
Sorry, what's L?
The unit sphere
In the
in the
KB2
Cayley
complex.
graphs. Right.
The KB2 complex.
So here it's a graph. So we consider only vertices which are distance one from identity, and the edges which connect them.
And triangular presentation.
Pardon?
Yeah.
No, I said it like
Oh, you
this.
said that we can.
If you have graph, it is okay.
And that's true for you don't.
The only thing you will see is the edges correspond to the triangular presentation.
You don't. Are you saying? Sorry, you don't. Do or do not need it to be a triangular presentation.
No, you don't need.
So
It just
free for any
other relation do not appear in L that I defined in one sentence.
It takes the inverse graph of unity or
That's right. So I'm taking the vertices are distance one from identity, and we consider on the edges which connect them. Okay. Right. Maybe now, because we started to talk, like when we start about this precise constant, it leads us to somehow, to the problem which is central for expanders, and which explains why there is so much interest in trying to understand expansion, to get new proofs. So I would like to talk now about the Zellberg conjecture. So we consider the hyperbolic plane and the Laplace Beltrami operator associated with this hyperbolic metric, and we'll consider the quotients of H2 by the congruence subgroups gamma n. So what Zellberg proved is that the spectral gap for this quotient for the glass operator acting on L2 on this arithmetic surfaces is this 360. Okay, which so they are we call them expanders. Actually translates to expansion property for the associated Cayley graphs of finite quotients of SLTZ by the congruence subgroups. Okay, and then there is a fascinating story concerning improvements. So what is the best possible estimate on lambda one could expect? Well, it's related to the spectral gap on H2. So the Zellberg conjecture is that the so of course, well, we have then this estimate, well, the same comparison result tells you that the limit Zuk for lambda 1 of H2 of the gamma n is at most 1/4, and the conjecture states that from the spectral point of view they are optimal. Okay, so let us compare it.
So is that a lim sub or all of them?
Pardon?
Is that that's each every one of them?
So the conjecture states that all of them, they have at least 4, and this little comparison results tells you that you cannot certainly improve. You cannot, it doesn't hold for any number bigger than 1/4. Okay, so now as here we compared isomorphic constant and lambda 1. So if we do the same for the hyperbolic upper half plane, so well, lambda is so the isomorphic constant for H2 is equal to 1. Okay, so the same like argument as we've seen here will tell you that the best you can hope for this finite quotient would be 1/2. Okay. However, so it was proven by joint work with Paul Brooks, is that the lim sup of H of the isomorphic constant for the surfaces right, when n tends to infinity is at most 0.46. Okay, so yeah, this is strictly less than 1/2. By the way, there are different models for random surfaces, and it's not clear if random surfaces are have better expansion properties. Okay, very good. Right. Maybe kind of what will the remark is that what enable one, for instance, to construct graphs with this remarkable spectral property, lambda 1, at least as large as this number, is the link between the representation theory and the spectrum of the discrete Laplace operator. So this is something that you know very well in the context of the of Lie groups, when the spectrum of the Casimir operator can parameterize all unitary family of unitary representations. What makes it so, and well, as you know, for the symmetric group, there is very well developed representation theory, which is very well understood. However, if you consider this Laplace operator, for instance, associated with 2 generators chosen at random, there is no direct link between representation theory and the spectrum of this operator, and that's what makes it so difficult to understand it. So what we do, maybe actually let me start with the let me say the result. So what we prove is that for a random choice of generators of the symmetric group, the mixing time is at most n cubed log n. Okay, and the way this result is obtained is as follows. So there is a link between the representation theory of Sn and the spectrum of the Laplace operator for when, as a set of generators, you take, for instance, conjugacy classes. For instance, if you take free cycles, then you can obtain precise formula for lambda 1. So the way this result is obtained is, first of all, you prove that with your pair of random generators, you will very quickly get all free cycles, and this follows from the expansion results for the action of Sn, say on triples of points. You can the same result we've seen with this geometric proof holds for the random graphs when you consider the action on the symmetric groups on k tuples of points. And then by combining this expansion results with the estimates on the spectral gap for the other set of generators, you are able to get this bound. So actually, maybe let me mention that these problems were stated a long time ago by Diaconis. And this matches the bound he predicted. Okay, thank you very much.
What do you mean? Did Diaconis study the same question? Exactly the same question, you mean? Or?
Right, so first of all, Diaconis studied many questions concerning Sn. So the most famous are the ones related really to shuffling. Okay? With the shuffling, of course, the number of generators tends to infinity. These are different kinds of questions. But he also studied this question, which is related to expanders. When you fix the number of generators, so that then for a fixed number of generators, that's the bound. Check too. Yeah, for some set of generators, you can pairs of generators, you can prove that this is exactly the right mixing time.
Can you translate your result into lambda 1?
I would prefer not, because it's not very interesting.
What if I ask you very nicely? I would really like it.
So it's I think I answered very nicely. Okay, so first of all, so the results where you get exactly, like precise, not estimate, but exact lambda 1 are, for instance, for the set of generators which are k cycles, then you get. And of course, these are set of generators such that the size goes to infinity. And moreover, you don't get the uniform spectral gap. Okay.
Do you have an estimate on how quickly you get the cycles for random choice of generators? And on the maximal length you need to use in those generators to get the cycles?
Right, yeah.
You get it?
Yeah. It fits from expansion, so you get exactly,
So
like the
what is
logarithm in the
the-
size.
Oh, I see.
Yeah.
Okay.
So do you have a concrete estimate, not like for random, but choice of generators, but for say Kasabov generators?
So for when you get right, so when you get the expansion, actually you can the mixing time you get is a logarithm of the size of the group, and so the ones you get exactly this one is the one which wouldn't give you expanders.
then how does the random choice of generators make your life easier here?
So here what is very important is the result concerning the expansion for the action on Sn on k tuples of point. Okay, the result, the Pinsker result, it's expansion when you take the action on Sn on n points. Okay, and it still holds if you consider the action on k tuples of different points.
Still, could you say more on that proof? So he's asking nicely.
So so instead of considering considering n points, you can choose from small take tuples of points. So I, j different. This will correspond to vertices of your graph, and you connect it to pi L of I, pi L of j. Okay, this is the graph that you build, and again here the random choice of a fixed number of permutation will lead to families of graphs which are expanders.
Right. To
However,
estimate the mixing time, we need that's kind of more numerical than. I mean, kind of the Shibu constant is just step one of the convolution. So we need to say something like you have a sum, right? Of mu to the n minus one.
Exactly.
And
So
there is something more analytic than just counting that you.
right. Yeah, exactly. So it's like yeah, it's like the first step trying to understand this notion, and indeed the techniques are much richer to deal with. It's not only just lambda one. Of course, you can once you've got like really expansion property, you get the best possible estimate. However, this analysis is much more interesting, and I would like to stress once again that you know small changes in your graph can with small changes you can lose this expansion property. However, it might not at all influence the mixing time. Okay, if it's just local change in your graph. So it's a really different behavior, and it's not, as you say, not just lambda one, but the whole spectrum, which is interesting in these considerations.
So there's no representation theory going into this thing because
There is a lot of representation theory. There is a representation theory. There is a lot of representation theory. However, as I indicated, you can do some work before you can use this information.
So if I understood you rightly, there's a sort of expansion phase and then a representation theory phase. Where you use
In this proof, right.
So you're saying that the mixing is preserved under small changes, but the expansion property isn't. You're saying this is the case for expanders.
That's right. Yeah, you
Because
can
there are
easily-
graphs where you can make small changes and have large changes.
Of course, yeah. That's right.
definition of expansion, one could replace lambda 1 or Cheever's constant by mixing time?
No.
No.
So as we said, you can this example with the small changes precisely tells you that you might not change mixing time, but you can change lambda 1. Your family of graphs might not be a family of expanders anymore. So, however, it's slightly different story if you talk about KD graphs, right? Where we cannot make these local changes, okay? By changing we make these changes everywhere. So, so the examples I mentioned are examples for graphs.
It sounds like you might be able to define a sort of weak expander or something by using mixing time, and then it might be a more robust notion of expander in the sense that
That's right.
change your expander a bit
That's
and
right.
get a weak expander.
And
Is there any chance that one could prove a version of your criterion with mixing time instead of lambda 1? I'm asking you very nicely.
right, so it's for this. So there are many tools, right, to deal with this with the mixing times. It's also so what you kind of what you ask for. It's there are very few results concerning the spectral properties for the graph, where you don't ask for expansion, but just some condition that lambda 1 would not go to 0 too fast. Okay, so
But that's what
this
your
would
thing is. I'm a little confused
would-
about this expansion. Your thing has nothing to do with expansion, family of expanders. This has to do with how the spectrum accumulates when you go to infinity, right?
Spectrum including higher eigenvalues, right?
Yeah.
So these high eigenvalues might play a role for short times. Yeah? When you go to infinity, it's just lambda 1, and indeed they play a role. Okay, so there is, of course, there is cutoff, a very interesting cutoff phenomenon which happens also. Finite time, I didn't have time to mention, but this is somehow it was really new input in this field of random walks.
In Zelberg's arguments,
With the
for lambda 1, he exploited just one representation, low-dimensional representation. Whereas here, in order to capture the full spectrum, you have to do something different. How does representation theory enter then?
So representation theory entered. You can get the exact value of lambda 1 for a very special set of generators for the symmetric group. Okay, for instance, for 3 cycles, okay, there is an exact formula, and so lambda 1 translates to some expansion property for this set of generators.
I mean, ideally, the representation theory enters if you analyze, if you take the non-abelian Fourier transform, you analyze your function mu, decompose it spectrally, you rewrite the whole thing. By the way, this sum, this is an L1 kind of thing.
Yeah, of course, you
Isn't
can
it
get estimates in other
for
LP. Yeah,
L2, yeah.
right.
I
But
wonder if L2 is not easier.
right.
Is it true in the definition of mixing time? So you just take a sum, it sounds like
That's
an
right,
L1
L1.
measurement.
Right.
So is this important? If you replace L1 by L2 sum, for instance, does it change the story?
Okay, so as I said, yeah, there was this constant. There is constant which is important when you talk about given group, yeah, like S52. And I would say, well, you might say that it's not really a mathematical question, yeah, but you asking about what is the right measurement and what is the right constant. Okay, this is the constant that is that appears here in statistics, but I think it's an interesting question whether it really says that you are close to the random permutation of cards, so that you could start a fair game. So there are these different distances for mixing time. This is the one which is admitted.
No, I agree that for in the Diaconis ideology, this points out to the definition you put, but if mathematically, if you would change the definition to an L2 sum, you might imagine that this makes things easier. And is this the case or not?
So of course there is
that this is changed asymptotic.
of course you get O for O piece you can consider it, and then you obtain different distances.
And different
Right.
asymptotics
Yeah.
as well. So